In the next few slides, we're going to cover the reactions that lead us to alcohols, and then later on, we're going to cover some of the reactions of alcohols. Alcohols can be interconverted with various functional groups, meaning we can go from an alcohol to one of these functional groups, or we can go backwards to the alcohol. And we're going to cover some of these reactions in the next few slides. One of the most common reactions to make alcohols is hydrating an alkene. Now we can do this a number of ways. We'll cover 3 different types of reactions. We'll start with acid-catalyzed electrophilic addition reactions, where we start with an alkene. We add an acid like sulfuric acid. We could also use phosphoric acid. And we must add also water as our source of the hydroxyl group. If we heat this up, we can convert an alkene into an alcohol. The typical alcohol that we obtain if we're starting with an unsymmetrical alkene is what we call the Markovnikov product. There are 2 possibilities for the alcohol. We can add the alcohol on the more substituted carbon, which would be this one, or the less substituted carbon, which would be this one. The Markovnikov rule, named after a Russian chemist from the 1800s, it says that in general, when we do an electrophilic addition reaction, meaning we're adding HX to an alkene, we generally add the hydrogen to the less substituted carbon. So in this example, it would be this carbon. And then we add the H group to the more substituted carbon. So in this example, the X group would be the hydroxyl group, so that would end on the more substituted carbon. The problem with acid-catalyzed hydration that we saw in the last slide is that we are limited to using very simple alcohols. So under the very strongly acidic conditions and the fact that we're heating it, many alkenes will polymerize or be converted to other functional groups rather than doing a hydration reaction. So when it comes to more complicated alkenes, very often we want to use an alternative reaction called the oxymercuration. Oxymercuration, as the name implies, uses a mercury reagent. One of the most common ones is mercury diacetate. We're going to add that to water, and typically this can be done at room temperature. If we add that to an alkene and then follow that up by sodium borohydride, which would convert a mercury intermediate into a hydrogen, we would end up with a Markovnikov alcohol. So similar product to what we saw with the acid-catalyzed reaction, where the alcohol ends up on the more substituted carbon if we start with an unsymmetrical alkene. Complementary reaction to the oxymercuration and acid-catalyzed hydration is hydroboration. Hydroboration gives an alcohol from an alkene, but it gives us the anti-Markovnikov product rather than the Markovnikov product. The reaction works by adding borane or BH3 to an alkene, followed by hydrogen peroxide and sodium hydroxide. That will convert an alkene into an alcohol. Generally, the alcohol will be on the less substituted carbon. So if this is our alkene, the alcohol would always be on this carbon, and then the more substituted carbon will have a hydrogen, which is not drawn out here. There's also a stereochemical component to this reaction where the hydrogen that is hidden will always be on the same side as the OH that we're adding. So this is called a syn addition of these 2 groups. So the hydrogen and the OH add from the same side of the alkene, which means if we originally had a methyl substituent or another substituent on the double bond, that substituent is forced to be trans to the alcohol. And so we end up with the trans product from this reaction due to the syn addition of a hydrogen on the more substituted carbon and this alcohol. Now is a good time to do a comparison between oxymercuration and hydroboration. If we start off with an unsymmetrical alkene, such as this example here, if we add BH3 or borane, which would give us this intermediate initially where the BH2 adds to the least substituted carbon, the hydrogen adds to the more substituted carbon. Notice there's a syn addition of these two new groups, followed by hydrogen peroxide and base, typically sodium hydroxide. We can convert this BH2 group into an alcohol. The stereochemistry doesn't change. We still have the OH syn to the hydrogen that just added. As a result, we end up with the trans 2-methyl-cyclohexanol because this alcohol is on the opposite side of the original methyl group that was on the double bond. Compare that to the oxymercuration. If we use mercury diacetate and water, we would add mercury acetate to the less substituted carbon, and we would add the water or the OH group to the more substituted carbon. So this would be a Markovnikov addition. If we then follow that up by sodium borohydride, it would convert this mercury acetate into a hydrogen. As a result, we end up with 1-methyl-cyclohexanol due to the Markovnikov addition of the hydroxyl group. Compare that to the anti-Markovnikov addition of the alcohol group in the hydroboration. This question, we want to predict the products from the following reaction. Notice this is an oxymercuration. We're using mercury diacetate and water, followed by sodium borohydride. We're starting off with an alkene, and notice it's an unsymmetrical alkene. Oxymercuration typically gives you a Markovnikov addition of an alcohol. So this alkene would be turned into an alcohol that has the alcohol on the more substituted carbon of the original double bond carbons. There will be a hydrogen being added to the less substituted carbon, though that hydrogen is not shown here since this is a skeletal structure.